So my topic for today is convolutional neural networks in view of sparse coding. And this is a joint work with Jeremiah Sulam, Yaniv Romano, and Professor Miki Elad. So according to Leo Breman, there are two cultures of people who work with data. These times called data scientists. The first culture is those people who believe in generative modeling, which means that you try to fit some sort of a model to your data, and then you try to do inference based on this generative model that explains the data. The second type of people is people who believe in predictive modeling, which is basically trying to solve the task at hand and trying to optimize the performance without caring about how the data was generated. Now, the main idea of generative modeling is to actually understand how the data was brought to life and how to actually operate on it under this understanding, basically. And the goal of predictive modeling is to win competitions. Now, in this course, we're all about understanding, so we're going to talk from now on about generative modeling. So what do I mean by generative modeling? So far we talked about the forward pass of CNN. And here you can see an example of an architecture that starts with an image, which is the first thing here. And then you convolve it with a bunch of filters. And the main idea is that the neurons that you obtain basically respond to edges in the first layer. Then you take the resulting three-dimensional volume and you convolve it with another set of filters to create another three-dimensional thing. And you apply ReLU and you convolve again, etc. And the main idea is that the neurons here would correspond to, let's say, eyes or noses. And if you go deeper, you would obtain neurons that correspond to faces. Now, when I say a generative model, what I mean intuitively is basically flipping this whole thing. So something that looks like that. So you would start with a vector that should encode a face by putting here a certain non-zero entry. And then you would multiply by certain matrices, apply certain operations to create three-dimensional volumes that would correspond to eyes and noses. And then you would apply certain other operations to create another three-dimensional volume that would create, let's say, edges. And then finally, you go from this three-dimensional volume to the image. So basically, you do all of the operations, but in the inverse order. Now, this is somewhat of a vague and intuitive explanation of what such generative models should do. Later, we'll see a much more precise description. Now, there's many questions that originate from the words generative model for CNN. The first question is, what generative model? Is there a generative model? Is there a single generative model? So in this course, we've already seen this gentleman, Ankit Patel, talk about the DRMM model. And in his case, he showed how the DRMM basically results in an inference stage that is nothing but the forward pass of CNN. Later, I'll explain what is the relation between this model and other generative models. The second question is, what properties should the generative model satisfy? So we had Tomasi Poggio in this class talk about how a function that goes from input images to different classes should satisfy certain properties for the case of dimensionality not to kill you, basically. And the properties are that this function has to be hierarchical, it has to be compositional, it has to be deep, and it has to be built from local functions. And all of these properties suggest that the generative model over here should satisfy them as well. Are these the only properties? Are there other properties that you should satisfy? We don't know. Another idea that we've seen throughout the lectures is the idea of Geoffrey Pennington, where he talked about how you can actually analyze CNNs by once you assume certain distribution on these weights that you're convolving the inputs with. So if you assume that these weights are ID Gaussian, and if you assume that these places of non-zeros, which are depicted in red, are independent between the different layers, then suddenly you can claim different things. Now, natural question to ask is, these filters right here correspond to certain filters right here. There's a certain match between the two because it's flipped, right? And here's a question. Can you propose a generative model where these filters are in fact ID Gaussian? Is it simple? Who knows? And can you have a generative model where the places of the non-zeros are in fact independent between the different layers? Is it possible? we've seen the lecture of Johan Bruno, who actually talked about overparameterization. So basically, he was telling you how if you take these filters and you increase the number of filters, increase their size, increase the number of filters, or whatever, suddenly the optimization problem becomes easier. Is there a way to explain such overparameterization from the perspective of a generative model? Not optimization, generative model. Another question, success of inference. So here's the story I'm selling you. I'm telling you you're starting with a vector, you're going all the way through this level of abstractions, and you're creating these three-dimensional feature maps. Then you're doing the reverse process. The first question you should ask yourself is this thing the same thing as this thing? Is this thing the same thing as this thing? Why do you care about such a question? Because if you can actually prove that you start with a certain vector that encodes a face, and then you generate an image, and then you obtain an image, and you go back to the original vector, and this original vector says a face, then basically you've managed to classify the image correctly. If you start with an image of a face, if you start with a vector of a face, you go to an image of a face, and then you say that this is in fact a dog, then you failed classification. By the way, I have here donuts. Whoever asks good questions will get a donut in the end. This is bribery. So another question is uniqueness of representations. So you're talking about generating data and then doing inference. And you're asking basically, can you go from this image to a certain feature map, and can this feature map be the same as this feature map? Now, if you're trying to go from an image to a feature map, this feature map has to be unique, right? Because if there were two different feature maps that can create the signal X, the image here, then it would make no sense to ask whether this thing can retrieve the original feature map that created it. I mean, if you had two different feature maps here that created the image, and then you're asking, can I take this image and go back to the feature map? If there are two feature maps, which one are you trying to recover? It's unclear. There's a question of stability. So imagine you take this image, you run the forward pass of CNN, and you obtain certain feature maps. Now imagine you start perturbing things. So you add some sort of noise here, right? And you're asking, how stable are these feature maps? So we've seen in this course the work of Helmut Bolsky, who talks about what happens once you perturb the input. And in his analysis, basically, he was saying that the distance between the original feature map and the perturbed one can be bounded using this constant that depends on the class of signals that you're looking at. But here's a question. Can you actually bound this distance between between the perturbed feature map and the original feature map in terms of a constant that depends on this generative model? Another question. We've seen the talk of Bruno Olshausen, who talked about possibly doing better inference algorithms. And these better inference algorithms should have information that would propagate both within and between the levels of representations. Can you actually give birth to such a better algorithm based on this generative model? Can you show that this generative model leads to different types of inference algorithms? And yet another question, can you actually do better training maybe? So we've seen Ankit Patel talk about how you can possibly train CNNs using the EM algorithm. We've seen Zaid Harchal, we talk about random feature, k-means, matrix factorization. All of these things, if you think about it, are just training algorithms that came to birth from generative models. So in this talk, I'm going to be focusing, as I said, on generative models. But I'm also going to focus on a particular class of generative models, one that is called the sparse representation. And the sparse representation, as we already mentioned in this course, all originated from the following observation, that receptive fields in V1 in the brain, in the visual cortex, have certain properties. They're spatially localized, oriented, and bandpass. And then came the work of Olshausen and Field, and basically showed that if you take natural image patches and you code them while promoting sparsity, you actually obtain the same filters that you have in the brain. And this led to 2 decades of vast theoretical study, a lot of different inference algorithms, and a lot of ways to train the model. And what I'm suggesting in this talk is, let's actually consider this as possibilities for improving CNN. Now, what I'm going to talk about is, I'm going to try and explain certain properties of convolutional neural nets. But in fact, convolutional neural nets are too hard to explain. So what I'm going to do is, I'm first going to look at the first layer of a convolutional neural network. But in fact, that's also hard, so I'm going to do another simplification. I'm going to start with the first layer of a fully connected neural network. I'm going to show the connection between this first layer of a neural network and the sparse representation model. I'm then going to show how you can extend this model to something which is called convolutional sparse representation, and this will shed some light on this thing. And then I'm going to show you yet another extension, which is called multi-layer convolutional sparse representation, which will basically explain this thing. So first layer of a fully connected neural network. What does it do? It takes an input x, it multiplies it by a certain weight matrix, which I denote by D transpose, and then it applies ReLU. And then you obtain an estimated feature map, right? Let's explain what is this thing in the view of sparse coding. So in sparse modeling, what you have is you have a certain family of signals. And let's assume these are patches of size 8 by 8 from natural images. What you can see, here's one example. And you assume that you have a certain dictionary. This is the dictionary, which contains different patches, or different basis vectors, or different atoms. There are different ways of naming these. And the main assumption is that every patch can be represented as the summation of only a few of these atoms. This is the sparsity. And there are two key properties. One is the sparsity, and the second is the redundancy, the fact that you are representing 8 by 8 patches which have 64 pixels using usually an complete set of atoms. So in a matrix notation form, what you have is X, which is a vectorized patch, which is a multiplication of a dictionary, which is overcomplete, as I just said. And this has different atoms. And this dictionary is multiplied by a sparse vector. OK. Now, given a signal X, a fundamental problem is atomic decomposition. Can you decompose this signal X to the atoms that construct it? Now, mathematically, you can write it as follows. You take the signal X, and you're trying to find a representation gamma, which has the minimal number of non-zeros, in such a way that X is equal to D gamma. Now, the thing about this problem is it's in fact very, very hard to solve because it's NP-hard. So what you do instead is you usually replace the nasty L0 norm with the pleasant convex L1. And then you obtain what is called the basis pursuit problem. Now, the thing is that we're impatient people, and we don't have time to do convex optimization to solve this whole thing. I mean, you need to do some sort of linear programming. So what you do instead is you can actually do some sort of crude approximation. So instead of solving this whole optimization problem, you just do one step of it, which is called the thresholding algorithm. And the intuition behind this algorithm is very simple. You take a signal X, and you multiply it first by the dictionary transpose, D transpose, and this computes correlation between different atoms, which are here in the rows, with the signal. And then you just zero all the entries which are below a certain threshold in absolute value. So basically, this is just a projection onto the L1 ball that imposes the sparsity. And then you obtain the estimated sparse representation. So this is crude sparse coding. Notice that the only difference between this algorithm, the thresholding, and the first layer of a fully connected neural network is the negative part. And in fact, there's different possibilities for the thresholding operator that you use. There is the soft thresholding that I mentioned, and another option is the soft non-negative thresholding, which basically assumes that all your coefficients are non-negative. And in that case, what you obtain is exactly ReLU with a certain threshold. OK, so now we move to the first layer of a convolutional neural network. So the first layer of a convolutional neural network takes an input image X and convolves it with a bunch of filters. And then you obtain some three-dimensional feature map that you pass through ReLU. And then you obtain an estimated feature map. And basically these blocks that you can see here are places which are non-zero, that ReLU didn't kill. The question... Halt if you don't get a cupcake. Yeah?
Just to clarify, so each plane is just looking at the convolution of one of these filters with the whole image, right?
Exactly.
And then you have many of those, so you call them filters. Okay.
Yeah, exactly. So you take this, you convolve it with the first filter, and you obtain the first slice in this three-dimensional thing. Okay, so then the question is, what is the corresponding sparse representation model? And the model is the following thing, which is called convolution sparse modeling, which has actually gained a lot of popularity in recent years in the signal image processing community. So in this case, what you assume is that your signal X is a multiplication of a dictionary, which is structured, times a sparse representation. And the structure that the dictionary has is that it is composed of different shifts of these local filters. So these little atoms or filters are basically like Gabor filters, shifted in different places in the image. In 2 dimensions, this assumption corresponds to assuming that your signal X is a summation of, this is the signal X, the image X, is a summation of different local filters convolved with sparse feature maps. So basically, this is D1, D2, D3, etc. And Z1 is the size of the image, and it's sparse. And Z2 is the size of image, and it's sparse. And you basically can put them into a single three-dimensional volume, as you can see here. Now, in TensorFlow, PyTorch, MatConvNet, whatever you use, you can actually write this equation in a single line of code. You just write it as X is equal to the convolution between gamma and the filters. That's it. One line of code. Now, imagine I give you a signal X that satisfies the convolution and sparse representation model. And imagine that I ask you, can you find the representation gamma? And please do it fast because I'm in a hurry. So what would you do? You would take a signal X, you would multiply it by a convolutional dictionary transpose, and you would apply the soft thresholding nonlinearity to obtain the estimated representation. Now, look at this thing, and imagine that you imposed, in addition, the assumption that the coefficients are non-negative. Then what happens is that this thing basically straightens, and you obtain ReLU. So what we see is now the first layer of a convolutional neural network. Why? Because we're taking a signal, we're convolving it with a bunch of filters in all the different positions, and we're applying ReLU. That's the first layer of a CNN. Okay, and finally we move to convolutional neural networks, which is what we care about. So in this case, we know that we take an image X, we convolve it with a bunch of filters and apply ReLU, and then we convolve this thing with a bunch of filters and apply ReLU again. And the question is, what is the corresponding sparse representation model? So here it is. In this model, you assume that your signal X is a multiplication of a convolutional dictionary times a sparse representation. So this is just a regular convolution sparse coding model. And you assume that the sparse representation itself is a multiplication of another convolutional dictionary times another sparse representation. Or in another way, you could put it as follows. You could say that you generate some global sparse vector gamma 2, you multiply it by D2 to create gamma 1, and then given gamma 1, you multiply it by D1 to create the image X. Let's remember again TensorFlow, PyTorch, etc. How do you write this in software? So here's how you do it. You take gamma 2, which is a three-dimensional cube, and you multiply it by D2 by doing a deconv operation. Then you obtain gamma 1. Then you take gamma 1 and you multiply by D1 to create X. Now, the reason I'm portraying it this way is because for some people this is easier to understand, because this is nothing but the decoder of an autoencoder, or the generator of a gun, or whatever you prefer. Okay, now imagine I'm giving you this signal X, and I'm asking you, can you actually retrieve these representations? And again, I'm in a hurry. I have no time to waste on convex optimization, linear programming, etc. So what would you do? You take the signal X and estimate gamma 1 by multiplying by D1 transpose and applying soft thresholding. Then you obtain an estimate of gamma 1, and then you would like to estimate gamma 2. What do? You take this, you multiply it by D2 transpose. And again, you apply soft thresholding and obtain an estimate of gamma 2. So what is this algorithm that we're seeing here? What is it doing? So basically, you're taking X, conv ReLU, right? So it's basically a convolutional neural network. You're taking X, convolving, applying ReLU, and you obtain your estimated representation. So by now, what should be clear is that the forward pass of CNN is a crude approximation of a sparse coding algorithm over this multi-layered convolutional sparse coding model. Any questions? Yes. By the way, I want to remind you the donut. How do you call it? Cupcake.
Is there any evidence that the activations in actual weakness are?
Awesome question. You'll see that yes. I'll show you at least 2 evidence. It's fine. Let the man have his cupcake. Yes?
So if I'm thinking of this as a generative model, I'm already thinking about all the nuisance parameters that I could have. Like I have a face, but I don't necessarily know where the center of the face is, and all of these things. Like this is something I'm kind of struggling to understand. You have you're starting kind of classes, and then there might be multiple kind of intermediaries that are generated.
Yeah.
At random.
Yeah.
And you want to end up back in the same class.
Yeah.
So with this kind of where does that
Randomness. Okay, so the randomness would be, I would say the randomness is in choosing the places of the non-zeros and their coefficients. So once you put a non-zero here, it means that there's a person here. Once you put a non-zero here, it means there's a car here. And this is a tree. So basically, you randomly pick, imagine you're constructing a scene, right? You randomly pick the locations in the spatial dimension. This is the spatial dimension. So you pick the tree should be here. Here you pick actually what kind of an object you're putting. But this is a higher level representation. Now, if you actually want to create the signal, the image of a car and a tree, you just need to multiply by the matrices and go to the image domain. Does this answer? Partially. Okay, so this course is on theories of deep learning. Thus far, I haven't presented any theory. So let's move to the theory part. So what I'm going to show you is the following idea. There's this sparse representation field, which I've shown an evolution of models from sparse representation to convolutional sparse representation to multi-layered convolutional sparse representation. Now, what we have is a theory of sparse representation. And we would like to use this theory to explain multi-layered convolutional neural networks. And to this end, what we need to do is take this theory and extend it to both convolutional sparse representation and multi-layered convolutional sparse representation. So let's do that. So again, imagine you have a signal x, which is a multiplication of d times gamma. And imagine that you are taking this x, and you're trying to find gamma by solving a basis pursuit problem. Now, here's a question. Is this estimated representation going to be the same one as the one that generated the signal x? It's a lovely question to ask, and a question that was answered in the past. So in the work of Professor Donoho and Professor Elad, they've shown that the basis pursuit algorithm, the one that you see here, is guaranteed to recover the true sparse vector if the true sparse vector is sparse enough. What is sparse enough? You can see here a certain term, which is half times 1 plus 1 over mu d. Mu of d is basically the mutual coherence of the dictionary. What is the mutual coherence of the dictionary? It's just the, okay, so to compute the mutual coherence, you take the dictionary and you multiply d transpose times d. And this thing is just computing the correlation between every 2 atoms in the dictionary. So you pick, let's say, a certain atom here, you multiply by a certain atom here, and you obtain a certain multiplication here. And the mutual coherence is defined to be the maximal inner product of 2 different atoms in absolute value. So it's the maximal entry, which is not on the main diagonal. And we assume that the filters are all normalized. Now, let's try to take this theorem, which proves that basis pursuit works under certain conditions, and apply it to this convolutional sparse representation model. Why? Because this is just a special case, so why not, right? Why should we work hard? So once you do that, you actually realize that it doesn't work so well, because if you have a convolutional dictionary which has two different atoms which shift in all the different positions, and these atoms are of length 64, you can show that the mutual coherence is lower bounded by a certain number. And this is using this Welsh bound. And then you can show that the number of non-zeros that you can allow here by plugging this here is basically 8. So what does this mean? It means that you can have 8 non-zeros in this whole huge vector. Now this vector can be of arbitrary size that depends on the spatial size of the signal. And the bigger the signal, the bigger the number of non-zeros is not. That's a weird way of putting it. It doesn't scale with the number of, with the dimension of the signal. So what we did in So we defined the idea of L0 infinity norm, which measures the maximal number of non-zeros in a neighborhood taken from the global feature map. So instead of saying, let's count the number of non-zeros in this whole three-dimensional cube, we're just measuring the number of non-zeros in this thing, which is 3. And we basically shift this in all the spatial locations and pick the maximal one. So we're basically assuming that there is no neighborhood which has more than a certain number of non-zeros. Now, why is this important? Because you can then define this new problem, which given x tries to minimize this new L0 infinity norm. And then you can actually use it to provide theory that is not completely pessimistic. So if you have a signal y which is close to a signal in the model, and if you solve the lasso problem, so basically minimizing L1, then you can show that if you are locally sparse, then the representation you estimate is close to the true one. Why is this important? Because instead of allowing 8 non-zeros globally, you can allow this number per each local neighborhood. So basically you can scale the number of non-zeros allowed with the dimension. And this is basically providing a theoretical guarantee for all these works that we're doing convolutional sparse coding in recent years. Okay, so our ultimate goal is to analyze this model, the multi-layered convolutional sparse representation. And to do that, we first define what is doing sparse coding in this model. So we define the deep coding problem. Given a signal x, this tries to find the representation gamma 1 to gamma L, where all of these representations are locally sparse. And you can also extend this definition to cases where you have some perturbation, model inaccuracies, etc. And then we ask several questions. One question is, given a signal x, is it possible that you can generate the signal x using gamma 2 and gamma 1, and also some different representation, gamma 2 hat and gamma 1 hat? Is the representation across the different layers unique? I mean, maybe you can take a circle, you can put gabors in different places, and then you can rearrange the gabors and suddenly obtain a different sort of representation. And what we show in our work is, in fact, if all the representations are sparse, locally sparse, then you can guarantee that these are the unique feature maps of X. Now notice that always what people ask is, how come? I train a CNN, I see that feature maps are different, so you're a liar. Not a liar, because the assumption here is that the model is fixed. Once the model is fixed, you can show that the feature maps are unique. But if the model is not fixed, then you hit in different models, and then per each model, the feature maps are unique for a signal. Okay, so
By model, you mean
yeah, the Ds, exactly. The dictionaries, the filters, etc. Now, here's another question. Imagine I give you a signal X, and I tell you that you're running the fourth pass, right? So right now we know that these things are unique under certain conditions. And you might ask yourself, is this algorithm managing to recover the representation that created the signal X? Is this thing the same thing as this thing? If they're not the same, can you at least claim that these boxes, the places that ReLU does not kill, are the same? So you can, in fact. You can show that if all the different representations are locally sparse, then this layered thresholding algorithm, which is the fourth pass of CNN, manages to find the places of the non-zeros correctly, and manages to find the values which are close to the true values. And the importance of this theorem is that it shows also limitations of this algorithm. First of all, this algorithm always fails no matter what you do. It will never manage to recover the original representations. It's not clear from the slides, but if you look at the theorem, you can see that. The second thing you can see is that the number of non-zeros that you can allow depends on this coefficient ratio. This thing basically measures what is the ratio between the minimal entry here and the maximal entry here. So if the entry is, one entry is like 1,000,000 and another entry is 0.1, then you're in bad condition. And basically you can see that if the ratio is not good, then the number of non-zeros you allow becomes smaller and smaller. And the last thing that you can see is that the distance between the estimated representation and the true one actually increases with the layer. I'm not writing the expression here because it's ugly. But if you look at the expression, you can see it immediately. So at this point, you should remember that what we have is a generative model that creates an image X, and then we're suggesting to crudely approximate the representations using the layered thresholding, which is the fourth pass. But what if we stop being lazy and we stop doing crude approximations and we do something which is better? So what if we do the layered lasso? The layered lasso is taking an input Y and then finding the sparse representation gamma by solving a lasso problem. Then you take the estimated gamma 1 and you estimate gamma 2 by solving another lasso problem. A cascade of lasso problems over several layers. Now, the nice thing about this whole generative model framework is that you can actually not only propose better algorithms, but you can actually analyze them. So you can provide a theorem that says that if all your representations are locally sparse, then this new algorithm is guaranteed to find only correct places of non-zeros and all the coefficients that are big enough, and is going to find a representation which is close to the true one. But most importantly, this algorithm is actually guaranteed to find exact representations under certain conditions. So under certain conditions, gamma hat is equal to gamma. Its success does not depend on the ratio, and the distance will still increase with the layer. So this is still a difficulty. Now you might be thinking, can you actually implement this in practice? And the way to implement that would be to take each lasso problem in each layer and solving it using some sort of the iterative thresholding algorithm, let's say, and then unfolding it and obtaining some very deep CNN. This is work in progress, so I'm not going to elaborate too much on that. But actually someone did something quite similar. This work of San et al. Basically did a cascade of lasso problems. It showed how you can actually backprop through lasso layers. And they show results which are actually on par with ResNext. ResNext is next generation of ResNet. So you can see 3.58 error, 5.81 error. But the number of parameters is 68 million in ResNext, and in the sparse coding variant, it's less than 1 million. So there is something to doing sparse coding apparently. Okay, so the generative model I'm showing you here is related to other works. Some we've seen in this course and others we've not. So here's again, the generative model is you take gamma 2, you multiply by D2, you obtain gamma 1. You take gamma 1, you multiply by D1, you obtain X, okay? So the first thing that comes to mind is GANs. Ian Goodfellow proposed this sort of architecture to train a generative model, I would say. So in his case, there's this generator here that basically creates images. What's the difference between this generator and the generative model I've been talking about? So the difference is that in his generative model, he takes this seed, multiplies it by a matrix, and then applies ReLU. Then he multiplies by another matrix and applies another ReLU. So basically, in his case, you obtain sparsification of all these three-dimensional feature maps using ReLU. And this means that it's a nonlinear generative model. There is another work, which is, as we already said, Ankit Patel. So in Ankit Patel's framework, if you look how he generates images, he takes a vector mu, let's say it's like a one-hot vector or something like that, and then he multiplies it by these matrices lambda. Lambda 1, lambda 2, lambda L. And each one of those matrices is a multiplication of two matrices. This is a convolutional dictionary in our language, and this is a binary random mask. So basically what he's doing is taking a vector, sparsifying it using a random mask, and then multiplying by a dictionary. then multiplying by another mask, multiplying by another dictionary. So he's obtaining the sparsification using a random mask. And there's actually a third work by Aurora et al. Who says, let's take a vector H, let's multiply it by a matrix W, and then let's apply both ReLU and a random mask. So he's applying both things. Yes?
So the random mask here is they all positive or non-negative?
The random mask,
Are they all 0, 1? Or?
I believe they are all 0, 1. So you can basically see the whole spectrum of ideas. You can see this generative model, which is linear. You can see this generative model, which applies ReLU. You can see this generative model, which applies random masks. And you can see this generative model that applies both random mask and ReLU. Which one is the simplest? The first one. Which one is the best? Time will tell. So finally, evidence. So okay, so we would like to see some evidence to what we've seen throughout this talk. So first of all, we already mentioned this again, all Southern fields, the filters look like that, right? And the reason you obtain these sort of filters is because you're imposing explicit sparsity. And in AlexNet, in the first layer, you're obtaining similar filters. Why is that? So my answer would be because you're using implicit sparsity. The fact that you're using ReLUs is basically saying that you're doing somewhat of a crude approximation of sparse coding, so you're pushing towards sparsity. Here's another interesting graph. In this graph, you can see the percentage of zeros versus the depth of a network for different architectures. And you can see that for no matter what architecture you use, at the end of the day, once you go deep enough, it becomes sparse. And it's one hell of a sparsity, 0.9. Here's another evidence. So in this case, what you can see is a person who he basically visualized a network. And what you're seeing here is what I call gamma 1. If you concatenate all of these things into one big three-dimensional volume, you obtain gamma 1. And you can see basically, you need to squint in order to see that this is white. Everything is basically black because it's zeros, because it's sparse. Now, if this is the first layer, if you go deeper, you can see, again, look how sparse. It's beautiful. Okay, so then the whole theoretical analysis assumed the mutual coherence is low, right? You might ask yourself, is the mutual coherence really low? So you can actually compute that, and this work of Shang at 2015 measured the average mutual coherence of the all convolutional network. And what they found is that if you look at the average mutual coherence, it's in fact not as bad as you might think. I mean, the mutual coherence goes between 0 and 1, where 0 is the best and 1 is the worst. And here you're obtaining values like 0.73. 0.073. Here's another interesting fact. There's a work which is called Parseval networks. This actually relates to one of the questions posted on Canvas. And this work is tackling the problem of adversarial examples. So adversarial examples is when you take a CNN, you feed an input image, and it says a cat. Then you slightly perturb in an adversarial way such that the network outputs suddenly an airplane. And the question is, can you do something with the network to make it more robust? So these guys had an interesting idea. They said, let's add this penalty to the objective that the CNN is minimizing. What is this penalty doing? It's basically minimizing the average mutual coherence, because this is a matrix which contains the correlation between all the different filters. And according to the theory I've presented, basically this means that you're going to be more robust to adversarial noise. And another example, so there's a recent paper, very, very recent, by Tomás Poggio, where he's talking about what happens in neural networks once you have objects which are close to each other. And basically it shows that this is a vulnerability, hard word to say, of CNNs. So basically this is somewhat suggesting that you should have CNNs where the feature maps are locally sparse, because local sparsity translates to crowding. If objects are near each other, you're not locally sparse. Okay, so let's summarize what we've seen. So we talked about how sparsity is a well-established idea, both theoretically and practically. We talked about how sparsity is covertly exploited in practice through nonlinearities such as ReLU, through tricks such as dropout, and through other things which I've not mentioned. We've talked about how sparsity is the secret sauce behind CNN. This is more like a prediction or a belief, in my opinion. And we talked about how you need to bring sparsity to the surface to possibly better understand CNNs, both sparsity and generative models. Now, if you don't trust me, you should trust Andrei Karpathy, who has the following to say. I'm not sure if you can listen here, but let's try. Can you hear? 1 second.
Yeah, I have to get sound.
Oh, there is no sound? I think it's worth waiting for what he has to say.
You have to have a. Do you have an audio jack? I don't know if you have. You don't have audio jack.
Oh, okay. You will forever be curious. Okay.
Just play it through your speaker.
Oh, maybe I can try that, yeah. Let's see if you can hear.
Put the mic next to well, the mic is only in the recording. Does that help?
Also to note, by the way, is that both dropout and ReLU are basically like 1 line or 2 lines of code to change. So it's about 2-line diff total in those 20 years. And both of them consist of setting things to 0. So with the ReLU, you set things to 0 when they're lower than 0. And with dropout, you set things to 0 at random. So it's a good idea to set things to 0. Apparently, that's what we've learned. So if you try to find a new cool algorithm, look for 1-line diffs that set something to 0. Probably will work. I could add you here to this list.
Okay, that's it. Thank you. Question?
Yeah, so while Dave is getting ready for the second part, let's go over the question. Yeah, next thing you have a question.
I have a question. So,
Yeah.
nice talk. So you
Thank
have
you.
several generative models, yours and all the other people have proposed. The main difference is yours is linear, the other ones are non-linear.
Yeah.
Do you think linear and non-linear are non-linear?
Do I think that linear versus...
Linear and non-linear play a big difference here. If you think about how an image is generated, if you, for example, you multiply the feature map by factor 2, do you expect the image to be multiplied by factor 2 as well?
Okay, so I would say that I believe in simple things, and you need to complicate only once you know that you need to complicate things. So I believe that you first need to explore the linear case before you go to nonlinear cases where you use ReLU, random masks, etc. I think that linear is simpler. It's definitely simpler to analyze. So I think that linear might be better, but it's all up to maybe practice to show what is the best thing. Out of all the works that I've shown, GANs are the only works that have actually generated images, right? So if you think practically, that's the way to go. But if you think theoretically, maybe GANs are not the way to go, because these are the works maybe that have the least to say in terms of generative models.
That very much depends on how you define the feature map, right? I mean, sometimes it makes sense to talk about the feature map being living in a linear space, you can scale it. Sometimes it doesn't. Sometimes the relationship of the feature map and an image are not a linear relationship. So that's why I'm saying that sometimes nonlinearity is probably needed.
Possibly, but I mean, I haven't seen something that proves that you should go nonlinear.
So,
Maybe you can have a cupcake. I'll give you.
next slide can give you the cupcake. So Ron Lysias is asking, one of your future direction in convolutional XML, be it convolutional sparse coding, is to try to reveal what are the benefits of introducing skip connections in ResNets. What does your intuition say about these benefits? And
Okay, so I didn't mention this, but there is a certain connection between ResNets and the layered lasso I showed you guys. If you try to actually depict the architecture of the layered lasso and ResNet, you might for a second think they're actually very similar. there are fundamental differences between the two. And there are a lot of similarities between the two. The differences you can see just by plotting the different architectures. But the similarities, I would say, you can see there is a work which, there's a few works that say the following idea. They say that in ResNet, you have a certain amount of layers with skip connections, and then you have another certain amount of layers with more skip connections. And what's dividing these two different groups is the stride. So you have, let's say, 4 layers, then you have stride, then you have 4 layers, then you have stride, 4 layers, stride, right? And I've seen certain works that claim that in those 4 layers, in that group, what's happening is that the feature maps are in some sense refined. Now, I haven't seen anyone who actually managed to explain what is this refinement process. But it somehow relates to the idea of layered lasso, where you have refined the representation. I'm not sure how much it answers the question, but that's my opinion on things.
So so we have some more minutes before Dave starts. Is there any question from the audience for Vardan can answer here?
Do you think that solving the lasso problem at each layer would be computationally better than doing gradient descent?
So there are 2 parts. There's the learning of the model, and there's the there are 2 parts. There's the training of the model, and there's the inference. What I'm talking about is the inference stage. Instead of doing the 4th pass, doing lasso. Instead of conv value in each stage of the 4th pass, do lasso. Do you see what I mean? So it's not replacing actually gradient descent.
Oh, okay, so it's you would use lasso to define the topology of your layers.
Exactly.
And then do gradient descent to refine the weights.
That's one possibility, yes. So then the problem is that if you're solving lasso in, let's say, I don't know, you have lasso block, right? How do you actually back propagate through lasso, right? That's a question. And this is a question that was answered if you look at the literature of sparse coding.
So let's thank Vardan.
So first of all, I want to thank everybody for persevering this whole quarter long. I think that we've had a number of very interesting talks, and it's a very vital and timely topic, as you shall soon see. Things happen on a daily basis in the Twitter sphere and in the blogosphere, which we will be mentioning. And this is giving us a chance here in the ivory towers of academe to be plugged into the larger concerns of what's going on in the rest of the world. For example, there's a meeting of NIPS right now, which is in Long Beach, California. There are 5,000 mostly industrial researchers there, impassioned about the goings-on with deep learning, and there have been some very controversial moments in the last 24 hours. Now, we've been listening to talks all quarter long, and we thought it would be important to try to take stock of what's happened, reflect on where we are, and maybe think about where we ought to be going in the future. One possibility is that the talks so far haven't really resolved anything. Namely, we're at a very early stage, and we've only gone a very short distance towards where we would like to be with theory. And so we don't have theories that are actually penetrating the big issues that we think need penetration. There's still the central mystery of why deep nets work so well, and why the enthusiasm that has been stimulated by computational experiments, why that should have happened. What is it that we can see in image content that makes this all come together? So if our speakers have not resolved all these central mysteries for us, then in a certain sense, as researchers, they've fallen short. And people in academia tend to judge others very harshly. So you could imagine that there's some penalty for researchers who fail to utterly solve the problems that they set out to solve. If so, there might be a potential penalty to be imposed on our speakers. However, I hope that we will judge them with a bit more indulgence, and we will just keep in mind that there are particular issues that we're just getting started with. Nevertheless, we'll come back to this a bit later because there might be a reason to bring this up in a certain assessment of what's gone on. Another way to assess what's gone on is that the world outside, namely the vast number of researchers assembled in Long Beach today at the NIPS conference, or in the corporate corridors of the Googleplex, at Facebook world headquarters just down the road in Menlo Park, that's now the establishment, and that the people who are trying to do theory are some kind of renegade, swashbuckling people with a kind of a crude and rough and ready attitude about how they're going to get their knowledge and going to approach these things. This was Hatef's idea, that we should glorify the theoretical pioneers who are out on the high sea with the salty air in their face and the waves of uncertainty crashing on them as they try to wrest a little bit of knowledge out of the experience that's out there. And then the course modification of crimes of deep learning would indicate that these are fundamentally transgressive people. By trying to bring in a theoretical viewpoint into what's otherwise a purely dry empirical subject, they're trying to turn it upside down and commit a kind of crime against the established order that all of corporate behemoths would instead want you to swallow. There's another point of view that we didn't get a fancy poster made for, which is that in the end, there are people who do deep learning in practice, and that those are in some sense playing a different game by different rules, and they're somehow unable to relate to the worldview of theorists, and likewise, theorists are unable to relate to the game as it's being played by the deepists, and therefore there's a fundamental antagonism between them. This idea came to us rather late in the game, but it's really borne out by events. It seems that there's a tendency in human groups for there to be polarization into binary formations of people who are on one side or on the other. And in this particular case, I think it would be unfortunate, but we do see signs of that tendency developing, as I'll show you shortly. And so in West Side Story, there's the Jets and the Sharks, and the passionate sharks, I think, here might be a good model for the theorist, as we're about to see, and then maybe the somewhat more smooth and composed Jets are something like the corporate deep learning empiricists. So far, we've got to give it to the deepists that they have the empirical success documented through contest victories, which are incontestable. And they're proving on a daily basis the unreasonable effectiveness of data, that by getting better, more copious, more ample data, you get better results, and you are able to crack open problems that people for decades and decades didn't believe would ever be approachable. On the other hand, theorists have behind them centuries of success in using formal models to understand very complicated systems, and in using the coherence of generative models combined with the inferences that they generate to have a very clear understanding of how to use data and learn from it. So there are traditions behind each of these, and there are important reasons that they can both be proud, but there are some fundamental differences in the mentality and the outlook of these, and that's partly expressed through the picture that I showed you here. There is some tendency to polarize. A nice example of this, I think Mickey Elad, Vardan's thesis advisor, had an opinion piece in Siam News several months ago called Deep, Deep Trouble, where he pointed to the fact that somehow deep learning is really causing trouble for the academics who do something that's theory-inspired, that we're not really able yet to come to grips with this whole phenomenon. And in example after example, Elad is able to show that there are these fantastic practical successes being achieved by deep learning, and there are a lot of grumpy theoretical practitioners who feel in some way threatened or unhappy with this state of affairs. At the same time, there's a meme that's out there, and has been out there for about 10 years, that the unreasonable effectiveness of data is going to kill theory. And one place that this became very prominent is in an article in Wired about 8 or 9 years ago. This article by Chris Anderson, then editor of Wired, brought forward very clearly the idea that if you have enough data, you don't need theory. By extension, you don't need theorists. Very recently, Wired continued the drumbeat and has talked ever more and more that actually we don't need understanding, and so obviously if you don't need understanding, you don't even need universities. Now at that point, I expect everyone to get up, just like all the villagers in the movie Frankenstein, 1938. Light your torches, take your pitchforks, and march on Facebook World Headquarters, and demand that the Frankenstein creations of deep learning be held back, because we can't be spoiling the happy life that we have here in universities simply to gratify their machine learning ambition. No, I'm not serious in that. But what I am serious about is that there's an inevitable tendency on the part of intellectuals to see some of these developments as threatening, confusing, and causing difficulties. Now, yesterday, there was a very nice moment at NIPS where Ben Recht and Ali Rahimi received an important award called the Test of Time Award for a paper that they wrote 10 years ago, in which they put forward the idea that you could make kernel methods much more computationally efficient by using what are called random features. So strategically chosen random vectors could be used to do the equivalent of support vector machines and the kernelization trick using an idea in some papers that they had developed. And after receiving the award, Ali Rahimi gave a presentation, which we will see an excerpt from shortly, and it really lit up the Twitter sphere, and people at NIPS yesterday, all they could talk about was comparing notes on their reaction to this. Now, I don't know if we have sound appropriately, so in fact, I don't even know how to turn on the sound here. I've got the thing plugged into audio, and
It works.
is there a sound somewhere? Okay, I'll just use the Mac sound just a second.
Bring it back.
It's now 2017, and the field has changed. We've made incredible progress. We are now reproducible. We share code freely and use common task benchmarks. We've also made incredible technological progress. Self-driving cars seem to be around the corner. Artificial intelligence tags photos, transcribes voicemails, translates documents, serves us ads. Billion-dollar companies are built on top of machine learning. In many ways, we're way better off than we were 10 years ago. And in some ways, we're worse off. There's a self-congratulatory feeling in the air. We say things like, machine learning is the new electricity. I'd like to offer another analogy. Machine learning has become alchemy. Now, alchemy is okay. Alchemy is not bad. There's a place for alchemy. Alchemy worked. Alchemists invented metallurgy, ways to dye textiles, our modern glass-making processes, and medications. Then again, alchemists also believed they could cure diseases with leeches and transmute base metals into gold. For the physics and chemistry of the 1700s, to usher in the sea change in our understanding of the universe that we now experience, scientists had to dismantle 2,000 years worth of alchemical theories. If you're building photo sharing systems, alchemy is okay. But we're beyond that now. We're building systems that govern healthcare and mediate our civic dialogue. We influence elections. I would like to live in a society whose systems are built on top of verifiable, rigorous, thorough knowledge, and not on alchemy. As aggravating as the NIPS rigor police was, I miss them, and I wish they'd come back. I'll give you examples of where this hurts us. How many of you have devised a deep net from scratch, architecture and all, and trained it from the ground up, and when it didn't work, you felt bad about yourself, like you did something wrong? Please raise your hand. This happens to me about every 3 months. And let me tell you, I don't think it's you. I don't think it's your fault. I think it's gradient descent's fault. I'll illustrate. I'm going to take the simplest deep net I can think of. It's a 2-layer linear net, so identity activation functions. And the labels are badly conditioned linear function to the inputs. On the left is my model. It's a product of 2 matrices that get taller, and they just multiply the input. And on the right is my loss function. And this is the progress of gradient descent and of various variants of it. It looks like gradient descent goes really fast at the beginning, and then it just seems to peter out. You might say this is a local minimum or a saddle point. That's not a local minimum, and it's not a saddle point. The gradient magnitudes are nowhere near 0. You might say it's hitting some statistical noise floor of the problem. That's not it either. This is not a statistical noise floor. I can compute the expectation of the loss, run gradient descent, and get the same curve. This is not due to randomness. Here's what a better descent direction would do. This is Levenberg-Marcotte. It gets down to 0 loss. It nails the solution in a few hundred iterations, and it gets to machine precision 0. If you haven't tried optimizing this problem, please take 10 minutes on your laptop and just try it. This is our workhorse. This is what we're building models around. You might say this is a contrived problem that badly conditioned something, and just the columns of this A matrix are correlated. That's the only weird thing about it. This is not a contrived problem. You might say gradient descent works just fine on more complicated, larger networks. Two answers. First, everybody who just raised their hands would probably disagree with you. And second, this is how we build knowledge. We apply our tools on simple, easy to analyze setups. We learn, and we work our way up in complexity. We seem to have just jumped our way up. This pain is real. Here's an email that landed in my inbox just a month ago. I'll read it out loud for you. It's from my friend Boris. On Friday, someone on another team changed the default rounding mode of some TensorFlow internals from truncate towards 0 to round to even. Our training broke. Our error rate went from less than 25% error to almost 99% error. I have several emails like this in my inbox, and you can find similar reports on various boards, on various bug reports on the public internet. This is happening because we apply brittle optimization techniques to lost surfaces we don't understand. And our solution is to add more mystery to an already mysterious technical stack. Batch norm is a way to speed up gradient descent. You insert batch norm between the layers of your deep net, and gradient descent goes faster. Now, I'm okay using technologies I don't understand. I got here on an airplane and I don't fully understand how airplanes work. But I take comfort knowing that there is an entire field of aeronautics dedicated to creating that understanding. Here's what we know about batch norm as a field. It works because it reduces internal covariate shift. Wouldn't you like to know why reducing internal covariate shift speeds up gradient descent? Wouldn't you like to see a theorem or an experiment? Wouldn't you like to see evidence that batch norm reduces internal covariate shift? Wouldn't you like to know what internal covariate shift is? Wouldn't you like to see a definition of it? Batch norm has become a foundational tool in how we build deep nets, and yet as a field we know almost nothing about it. Machine learning has taken a new spot in society. If any of what I've been saying resonates with you, let me offer just two ways we can assume this new position responsibly. Think about, in the past year, the experiments you ran where you were jockeying for position on a leaderboard and trying out different techniques to see if they could give you an edge in performance. And now, think about, in the past year, the experiments you ran where you were chasing down an explanation for a strange phenomenon you'd observed. You were trying to find the root cause for something weird. We do a lot of the former kind of experiments. We could use a lot more of the latter. Simple experiments, simple theorems are the building blocks that help us understand more complicated systems. Here's a second thing we could do. Right now, our mature computational engines that run on commodity hardware are all variants of gradient descent. That's what we have that can handle tens of billions of variables. Imagine if we had linear system solvers or matrix factorization engines that could handle tens of billions of variables and operate on commodity hardware. Imagine the amazing kinds of optimization algorithms we could build. Imagine the incredible models we could experiment with. Of course, it's a hard math problem and it's a hard systems problem. But this is exactly the group that can solve these problems. Over the years, many of my dearest relationships have emerged from this community. My affection and respect for this group are sincere, and that's why I'm up here asking us to be more rigorous, less alchemical, better. Ben and I are grateful for the award and the opportunity to have gotten to know many of you and to have worked with many of you. And we would love it if we could work together to take machine learning from alchemy and into electricity.
So as I said, after that, you can go to Twitter and search Ali Rahimi, and you can see all sorts of interesting commentary. And so here, Frank McSherry says, a great test of time talk by Ali Rahimi, distilling what is the main reason I've stayed away from the area of late. Learning research can be more art than science. Zachary Lipton, Ali Rahimi delivered a rare critical talk at NIPS 2017 likening modern ML to alchemy. Examples, brittleness of SGD to implementation changes, and mystical claims like batch norm works by reducing internal covariate shift, etc. We only showed 2/3 of that. The first third, he was talking about how NIPS, I had the same experience as he did, by the way. NIPS used to be fun. There were theorists, there was the rigor police, and there was skiing. It's all gone. It's all a big confab of let's say, deep learning people and people who are interested in industrial priorities and so on and so forth. Now, Jan LeCun didn't take too long to respond, and I want to say, first of all, that Jan, over the years, has anyone associated with machine learning, I think he's been the most prominent that I know of as at encouraging the development of theory. So he's sent me papers to review, and he's acted in a very beneficent way towards people who tried to come up with theories that explained important phenomena within ML. So it's not like he's someone who would be antagonized by a theorist in some natural sense, but he didn't like this presentation. So here, my take on Ali Rahimi's Test of Time award talk. He gave an entertaining and well-delivered talk, but I fundamentally disagree with the message. The main message was, in essence, that the current practice in machine learning is akin to alchemy, his word. It's insulting, but never mind that. It's wrong. In the history of science and technology, the engineering artifacts have almost always preceded the theoretical understanding. The lens and the telescope preceded optics theory, the steam engine preceded thermodynamics, the airplane preceded flight aerodynamics, radio and data communication preceded information theory, the computer preceded computer science. Why? Because theorists will spontaneously study simple phenomena and will not be enticed to study more complex ones until there's a practical importance to it. Criticizing an entire community, and an incredibly successful one at that, for practicing alchemy simply because our current theoretical tools haven't caught up with our practice is dangerous. Why dangerous? It's exactly this kind of attitude that led the ML community to abandon neural nets for over 10 years, despite ample empirical evidence that they work very well in many situations. So he's speaking here about the fact that neural nets, say from 1998 until about 2008, were eclipsed by SVM in various ways. So kernel methods took over for a while. Neural nets with their non-convex loss functions had no guarantees of convergence, though they did work in practice as they do now. So people threw the baby with the bathwater and focused on provable convex methods or glorified template matching methods or even 1957 style random feature methods. That's a subtle dig at Ben and Ali. Sticking to a set of methods just because you can do theory about it while ignoring a set of methods that empirically work better just because you don't yet understand them theoretically is akin to looking for your lost car keys under the street like knowing you lost them someplace else. Yes, we need better understanding of our methods, but the correct attitude is to attempt to fix a situation, not to insult the whole community for not having succeeded in fixing it yet. This is like criticizing James Watt for not being Carnot or Helmholtz. Ali, if you are not happy with our understanding of the methods you use every day, fix it. Work on the theory of deep learning instead of complaining that others don't do it, and instead of suggesting the good old NIPS world was a better place when we used only theoretically correct methods. It wasn't. Ali Rahimi next comes back. So by the way, as you might imagine, Jan LeCun's post was not on Twitter. It was on a Facebook page, and you can find that at Facebook. Ali Rahimi then answered back, Jan, thanks for the thoughtful reaction. If you don't like what's happening, fix it is exactly what Moritz Hart told me a year ago. It's been hard to make progress with just a small group, and to be honest, I'm overwhelmed by the scale of the task. The talk was a plea for others to help. I don't think the problem is one of theory. Math for math's sake won't help. Ooh. The problem is one of pedagogy. I'm asking for simple experiments and simple theorems so we can all communicate the insights without confusion. You've probably gotten so good at building deep models because you've run more experiments than almost any of us. Imagine the confusion of a newcomer to the field. What we do looks like magic because we don't talk in terms of small building blocks. We talk about the entire models working as a whole. It's a mystifying onboarding process. And I agree that alchemical approaches are important. They speed us up, they fix immediate problems. I have the deepest respect for people who quickly build intuitions in their head and build systems that work. You and many of my colleagues have this impressive skill. You're a rare breed. Part of my call to rigor is for those who are good at this alchemical way of thinking to provide pedagogical nuggets to the rest of us so we can approach your level of productivity. The rigor I'm asking for are the pedagogical nuggets, simple experiments, and simple theorems. Well, there's quite a lot there that we could discuss and react to, but I just thought we could talk about one aspect that came up in this discussion that is worth pointing to. Oh, by the way, I didn't mention this before, but I want to thank XY Han, Zhaoyan Han, who downloaded the video and excerpted it and made it available for us all to watch. Thank you, XY. We had a course this quarter, Massive Computational Experiments, Painlessly, where we discussed everything that you could do with modern technology to easily run ambitious computational experiments. And if you know the course website for 385, it's just the same URL, just change 385 to 285, and you'll get a parallel website which has a lot of information. The relevance here is that we taught everyone that we're in a new place in world history, that because peasants and teenage girls have smartphones and we're in this new image-drenched world, we've developed a fantastic information technology infrastructure which makes it possible for researchers in academia and industry to harness unbelievable amounts of computing power, practically trivially, that are located in data centers all over the world, but for example, above the Arctic Circle. And the message that we tried to communicate in that particular course is that, roughly speaking, you can visualize running ambitious experiments that are happening in a data center somewhere, and the results are just streaming right into a paper that goes into some charismatic destination for your research. So we discussed this. We had a series of interesting lectures, and a very important one, which is sort of the culmination, was last week, given by Hatef Monajemi, a postdoc in the stat department, push-button deep learning on the cloud. And the basic idea is there are two commands you could give, and you could run any of the deep learning models, training on any of the data sets that we're talking about with sort of minimal editing and preparation, minimal effort on your part. In that lecture, what was culminated was a 10-week series of guest lectures where we taught students about the cloud revolution and resources and how these phenomena like AWS, which currently has 6 million cores available for use, how they had arisen because of smartphones and infrastructure. We assigned students homework using cloud resources. Google, via its Google Cloud Platform, provided the compute resources for our students to do ample amounts of computing. They gave $400 budget per student, which is quite a lot. One CPU hour costs about 3 cents. So $400 will go a long way. Students, as a class project, jointly performed a massive deep learning experiment in which every different popular, famous deep learning model was used on every different data set, and they were torture tested under a range of conditions that probably they hadn't been torture tested, most of them, on before, where the labels for the classifiers were corrupted in various ways. The research design done in this way is similar to meta-research that's popular in epidemiology and observational biostats. So we were bringing ideas of running very highly compute ambitious things as a grid of a complicated cross design on top of individual complicated training experiments on top of switching out various data sets. This is a lot of stuff going on here, all funded by Google. Thank you very much, Google. In this assignment 02, which you can go look at our website, you get all the instructions to run an ambitious experiment on the cloud. You're taught how to do it, and you're even told how to go get free money from Google to do it using your Stanford ID. Now, the reason that this is relevant is I want to point out that Ali Rahimi said many times he wants to see experiments. In fact, he said simple experiments, but experiments of any kind would be useful. We're starting to see that. And in fact, one of the most highly quoted papers in deep learning of the last year or two is this paper by Qiyuan Zhang, Sami Bengio, Moritz Hart, Ben Rex, and Oriol Vinyals. Several of those names are pretty known in deep learning, and Ben Rex's name you heard earlier today. In this example, they did some very interesting experiments where they, in some sense, damaged the training process of a deep net to see what would happen. So they viewed a deep net in the same way that you would, a biological specimen, and they did stuff to it. And that paper became extremely prominent and widely quoted. And I think that the experimental aspect of, let's understand how these systems behave when they're probed in certain ways, and then let's try to develop a theory that explains what we see. That was fresh, and people do believe there's a need for that. We're starting to see a number of other interesting results coming along. So here is one of these complex studies similar to the one that we did in Stats 285. It was submitted last week as we we're assigning a similar type of experiment to the Stats 285 class. So things happen very quickly and intensely in this area. What they did here is they considered many GAN algorithms, and they tried across many data sets, and they concluded that most models can reach similar scores with enough hyperparameter optimization and random restarts. This suggests that improvements arise from a higher computational budget and tuning more than from fundamental algorithmic changes. Finally, we did not find evidence that any of the tested algorithms consistently outperforms the original one. So this is saying something important, which is that there are many individual authors with claims for their GANs as being in some way fresh, original, interesting. But at a meta level, there's not much evidence of a difference between these algorithms in their consistent performance. And that it takes a very rigorous attention to detail in order to resolve improvements due to architecture and other algorithmic ingredients. Another recent paper, this is 2 months old, so it's practically ancient in this field, but this one considered reinforcement learning and again talked about the lack of reproducibility in the field and the lack of consistent ways of measuring progress, and promoted the idea of doing things with reproducibility, following experimental techniques, so that actually we would know whether reinforcement learning was seeing progress or not. And the kind of claims that are out there that are in some ways confusing, which is what Ali Rahimi was talking about, this actually backs this up with evidence that there's a lot of overclaiming going on and not enough research that's with a sufficient level of rigor. So back to our posters, I think one thing that theorists could do is combine their theoretical insights with the design and carrying out of critical experiments. I think that theorists have not wanted to get very involved in the experimental fray to this point, and maybe because it looked too painful. But as I think we've proven in Stats 285, and by the way, Amazon is proving through making available its SageMaker software, which automates a lot of machine learning experimentation. It's becoming easy. It's happening very, very quickly. And this experimental approach is now possible. Theorists, if they have a good idea for an experiment, can do something decisive quite quickly at this point. And so it's time for theorists to get in at a new level of engagement where they're actually doing machine learning experiments, they're actually getting their hands dirty with training and so on and so forth, testing out their ideas very explicitly. Now, there's long been a split between theorists and practitioners. And in the 18th century, we saw a kind of polarization between rationalists who believed that it was possible simply by thinking about things to arrive at the true story of anything, and empiricists who said you have to take sense data, process them, and see what the sense data mean. In the end, the story was that empiricists have won over the narrow rationalists. But what's really been a win is when there was no polarization, and instead the rationalists combined with the empiricists, that there was theory to explain the empirical results, and there were empirical results to inspire new theory. If the theorists that we've seen are not going to get engaged with experiments and not going to try to propose critical experiments which will test out their theoretical ideas, then they're trapped truly in the same area where Leibniz and all the other rationalists were trapped, trying to derive solely from their own mind the way things ought to go. It's the hybridization of the experience together with the theory which will lead to practice. If we have this kind of polarization in the way that we saw with the two gangs in West Side Story, that one of them is drawing a knife against the other, and we see this kind of conflict as started to develop between Ali Rahimi and Jan LeCun, I think everything will go south here. We want to avoid polarization. We want to achieve some kind of hybridization and interplay between these two areas. The great thing is that the computations are becoming much easier, and it's much easier now for theorists to engage with this than, say, 10 years ago when this was getting started. I'm looking forward to seeing all those who've made a theoretical investment to continue with all the creative ideas that they've been proposing, but to do them in a fruitful engagement with practical experiment. Thanks for your attention in the whole course. I've really enjoyed it, and I hope you have as well.